Look at the agricultural output of the Indian subcontinent, and you will see a massive, seemingly random distribution of crops. Punjab produces massive surpluses of wheat, while Assam grows thick plantations of tea. This geography of food is not an accident of nature, it is entirely deterministic. The entire landmass is divided into 6 major soil zones: alluvial, black, red and yellow, laterite, arid, and forest soils. Understanding why these zones exist where they do requires viewing soil as an active, highly localized chemical and physical process. You can reduce this process to a single geoclimatic equation. If you combine a region's base geological origin with its local climate, you get the specific physical and chemical traits of the soil. The first variable, geological origin, provides the raw elemental material. It determines exactly which minerals and metals are locked inside the local bedrock. The second variable, climate, acts as the weathering engine. Heat, wind, and rainfall dictate exactly how fast and in what manner those raw rocks break down over thousands of years. The resulting texture and chemical makeup of that broken down rock form a strict biological boundary for what crops can actually survive there. By reverse engineering this formula, you can look at an entirely blank map of India and accurately predict exactly where its food will be grown. Looking at these immense snow-capped peaks, we find the starting point for India's most important agricultural resource, the high-altitude, cold climate of the Himalayas. 3 massive river systems, the Indus, the Ganga, and the Brahmaputra, drop thousands of feet through this mountain range, generating incredible kinetic energy. These turbulent, fast-moving waters physically shatter the bedrock, picking up massive amounts of heavy particulate matter and dragging it downward. This calm river and its massive sandy banks show the depositional end state of that kinetic energy. When the rivers reach the tropical and subtropical northern plains and coastal deltas, they lose momentum and drop their sediment. We call this loamy mixture of sand, silt, and clay alluvial soil. This cross-section shows the dual nature of alluvial regions. The older, coarser soil forms an elevated terrace called Bangar, while the lower floodplains are constantly renewed with a finer, highly fertile layer of sediment known as Khadar. Because of its Himalayan origin, this Khadar layer provides a precise chemical profile, a rich blend of potash, phosphoric acid, and lime. However, it remains severely deficient in nitrogen. This exact chemical cocktail dictates the region's agricultural destiny. That specific combination of available nutrients, combined with the loamy texture, biologically limits the plains of Punjab, Haryana, and Uttar Pradesh to crops that thrive in those exact conditions, primarily rice, sugarcane, and pulses. These bundles of harvested wheat are the ultimate result of that depositional network. Alluvial soil is not formed where it sits. It is imported geological fertility, and that continuous importation makes it the most agriculturally significant soil in India. To see a completely different pedological engine, we shift south to peninsular India. This wide, tiered landscape is the Deccan Trap. It is a massive expanse of dense volcanic basalt rock. Unlike the imported alluvial plains, this region relies entirely on in situ formation. The material is never transported by rivers. It degrades right where it sits. The semi-arid and dry climate of the plateau slowly weathers the basalt, breaking it down in place to create black soil, traditionally known as Ragar. Because of its volcanic origin, Ragar has entirely different physical mechanics. It is extremely fine-grained and clayey. It expands and becomes incredibly sticky when wet, and as summer heat hits, it contracts to form deep geometric fissures. Chemically, the weathered basalt leaves behind a soil rich in calcium carbonate, magnesium, and potash, but severely poor in phosphoric acid. Those deep summer cracks allow the soil to aerate naturally, while the dense clay holds moisture tightly during dry spells. That water retention, combined with the high calcium and magnesium, makes this the ultimate environment for growing cotton. But if you move to the eastern and southern edges of the plateau, the bedrock changes to crystalline, igneous, and metamorphic rock. This split screen shows what happens next. Under areas of low rainfall, iron trapped inside the crystalline rock diffuses outward. This creates red and yellow soil, porous, shallow, and highly acidic. Because it lacks moisture retention and humus, it supports hardy crops like millets and groundnuts. Two adjacent geographical zones yield drastically different agricultural outputs, governed entirely by the hidden bedrock beneath them. Now, consider what happens when extreme weather overpowers geological origin. Looking at these deeply green, heavily forested valleys of the Western Ghats, we find an environment of intense, heavy rainfall. This environment creates laterite soil. The region suffers from extreme environmental stress caused by alternating wet and dry monsoon seasons. This cross-section shows the mechanical result: intense leaching. The sheer volume of heavy rain physically washes critical nutrients, like nitrogen and potassium, deep underground, away from plant roots. It leaves behind a crumbly, highly acidic top layer. As you see with these workers, this naturally infertile soil requires heavy management, but its specific coarse texture perfectly supports deep-rooted plantation cash crops like tea and coffee. Moving from extreme wet to extreme dry, we find the hot, arid climate of Rajasthan and Gujarat. Here, intense heat and wind deposition weather the local red rocks into a loose, sandy matrix known as arid soil. This creates a hidden geographical trap. Just beneath the loose sand forms a conchar layer, a solid calcium deposit that physically blocks water from percolating down into the deep earth. When rare water hits this conchar layer under intense heat, it rapidly evaporates back upward. This pulls salts to the surface, creating a highly saline, alkaline profile devoid of organic matter. Conversely, in the cold, humid mountainous zones of the Himalayas and high-altitude Ghats, temperature acts as a different kind of filter, creating forest soil. Here, the steep topography physically alters the texture. You find rich, loamy, and silty soil trapped in the valley floors, while the steep alpine slopes retain only coarse, gravelly fragments. Without the heat to drive rapid decomposition, fertility fluctuates wildly. Dense forests create rich humus, while sparse, high-altitude ridges remain highly acidic and infertile. On these geographical fringes, climate acts as a destructive force, stripping base nutrients away and forcing agriculture to adapt to the extremes. We can now look at the fully populated map of India, matching these 6 distinct soil types directly to their geographic regions. The base rule holds. Geology plus climate creates an unbreakable boundary for agricultural limits. But there is a final, critical caveat to this deductive model: human intervention. Consider laterite soil again. In its natural state, it is a highly acidic, heavily leached environment hostile to most staple crops. But by introducing modern chemical fertilization and strict soil improvement techniques, agronomists overwrite that natural infertility, transforming the hills of Kerala and Karnataka into a lucrative engine for tea and cashew nuts. Or return to the hostile, saline, arid soils of the Thar Desert. This massive human engineering project, the Indira Gandhi Canal, cuts directly through the scrubland to sever those environmental constraints entirely. By supplying a constant artificial water supply, engineers bypass the conchar percolation barrier. That steady irrigation flushes the salinity and transforms sterile sand into productive, profitable fields of barley and wheat. Ultimately, these soil classifications provide a precise baseline for strategic resource management, codifying thousands of years of geological history into actionable data. Final takeaway: true agricultural dominance in India comes first from understanding the rigid laws of pedogenesis, and second from engineering the tools to break them.